Welcome to the new phase of benchtop chemistry. Today, we'll talk about the brilliance of bringing the fascinating world of quantum dots into spotlight. The Royal Swedish Academy of Sciences decided to award the Nobel Prize in Chemistry 2023 to Moungi Bawendi from MIT Cambridge, Louis E. Brus from Columbia University, New York, and Alexei Ekimov from Nanocrystals Technology Inc., New York, for the discovery and synthesis of quantum dots. This Nobel Prize rewards the discovery and development of quantum dots, nanoparticles so tiny that their size determines their properties. Now let's try to understand as to what are these quantum dots. Everyone who has studied chemistry must have learned that an element's properties are governed by how many electrons it has. However, when matter shrinks to nano dimensions, quantum phenomena arises. These are governed by the size of matter actually. Let's make it more simpler. A quantum dot is a semiconductor whose excitons are confined in all the three spatial dimensions. We have two dependable words here, excitons and confined. So let's go into the details of these two terminologies. In a semiconductor material, when an electron absorbs the energy, maybe through the absorption of photons or thermal excitation, then what happens? It moves from valence band to the conduction band, which is actually a region where electrons can move freely. When this happens, it leaves behind an empty space known as hole in the valence band. Now this hole and the electron can interact with each other due to opposite charges, forming a bounded state known as exciton. Now these electrons and the whole pair or the excitons tend to stay relatively close to each other within the semiconductor material. They don't roam freely throughout the material but are restricted to the limited region, or we can say that they are localized or confined within the semiconductor material in all the three spatial dimensions, that is length, width and height. This confinement of excitons plays a pivotal role in the unique properties and the applications of quantum dots. So the story so far tells us that the quantum dots are extremely small structures, usually ranging from 2 to 10 nanometers in diameter. Within the regime of these critical nanoscale dimensions, quantum dots exhibit distinctly different behavior from their bulk form in optical, electronics, and magnetic properties. Generally, quantum dots fall into the category of nanocrystals. Now, the energy band gap of quantum dots depends on the particle size of the material. This aspect is the most predominant feature of quantum dots. By changing the particle size, the band gap will change and so will the color of the light emitted. This occurs because the specific wavelength of light emitted is a function of the band gap energy. One of the most striking features of quantum dots is their ability to emit the light of different colors depending upon their size, a phenomena which is called as quantum confinement. Basically, let's try to understand this quantum confinement. Suppose we have a bulk material. The yellow cube that we can see over here is our bulk material. That means the size of this material lies beyond the nanoscale, that means greater than nanoscale. Okay, so when the bulk material is taken, then obviously it is made up of huge number of atoms and each one is having its own energy band. So we can see over here in the figure also that the difference or the energy band, when it's broken into discrete levels, So what happens? The valence band and the conduction band, which are present in that particular bulk material, the energy gap between these valence band and the conduction band is represented by capital E over here. Now let's try to figure it out when I reduce the size of this bulk material to nanoscale. So I have reduced my particle size. So what happens? Actually, when the bulk material is reduced to the size of nanoscale, the energy band is broken into discrete levels so that the energy band gap is widened, as you can see in the figure on the right hand side. The value of E has changed. The band gap has widened up. This means that both absorption and emission wavelength of the light become shorter. The smaller the size of quantum dots, larger is the band gap energy. Thus, we can say that by simply altering the size of materials, that means changing the size of materials, let's say bringing it to the nanoscale, the energy band gap can be changed, and accordingly the color of the light emitted can be changed, as we can see in our next figure. The spherical balls have a numeric figure marked on them, which actually represents their size in nanometers. So the size of these particles from left to right is increasing from 2 to 2.5 nanometers and then 3, 5 and 6 nanometers respectively. Now what I have done is I have subjected all these nanoparticle size samples with the same blue light having the wavelength of approximately 450 nanometers. Now what happens when this light passes through these respective samples, 5 different samples having 5 different size of the particles, then what we see, the emitted light colors changes. It is no more blue, and to our surprise, each sample is giving us a different color of the emitted light. So the wavelength changes, actually it increases. So this is what is happening over here. We can change the color of the reflected light. We can change the color of the emitted light by changing the size of the particle. This actually is an explanation of quantum confinement application. Let's try to summarize quantum confinement over here. We discussed so far that as we decrease the size of the bulk material and bring it to the nanoscale, then what happens? The number of atoms decreases, and obviously when the number of atoms decreases, then the number of energy levels also are less. In other words, in nanoscale materials, the quantum confinement causes the energy levels to become discrete or quantized. This means that the electrons can only occupy certain specific energy states, and there is a significant energy gap between these states. Quantum confinement effects are more prominent when the size of the material is on the nanoscale, typically a few nanometers or rather smaller than that. In other words, we can say that the size should be comparable to or smaller than the wavelength of the particles, for example, electrons in that particular material. So the smaller the size of the crystal, the higher will be the energy of electron. Its kinetic energy is increased because of that, and that can be thought of as making its wavelength a bit shorter and forcing it into a box where it's kind of zips around more quickly. It moves around more quickly. So the size of the nanomaterial directly influences the energy levels. After understanding the quantum dots and its specific properties, now let's try to have a look of what our Nobel laureates have done. Alexei Ekimov in 1980s, he was successful in creating size-dependent quantum effects in colored glass using copper chloride. Actually, what happened? The color came from the nanoparticles of copper chloride, and Ekimov demonstrated that the size of the particle was affecting the color of the glass via quantum effects, just like we learned about in our previous slides. A few years later, Louis Brus was the first scientist in the world to prove the size-dependent quantum effects in particles floating freely in a fluid. And thereupon in 1993, Bawendi revolutionized the chemical production of quantum dots, resulting in almost perfect particles. This high quality was necessary for them to be utilized in applications. So, in short, our Nobel laureates in chemistry 2023 have succeeded in producing particles so small that their properties are determined by quantum phenomena. And these particles are the quantum dots. Hope you enjoyed today's journey with us. Catch you soon.